Our question: if B and C is relative prime means there is no common divisor of B and C greater than 1. Then if you multiply B and C and take GCD with another number, then GCD of A and B multiplied GCD of A and C must be equal. For clear understanding, we take a common example. For example, I have two numbers, two relative prime numbers, 3 and 5. Okay, if here suppose this is B, this is B, and this is C, they are relative prime. If I multiply these two numbers, 3 multiply 5, this is BC. I have BC here. I multiply 3 and 5. Take any other number. For example, I take 6. This is A. Then what will be the GCD of A and BC? Okay. Here we have 6 and 15. So what is the greatest common divisor of 6 and 15? 3. And now we take AB. What is A? 6. And B is 3. What is the greatest common divisor of 3 and 6? Is 3. And now I take 6 again. This is A and B. Okay. And now I take A and C. What is A? 6 and C is 5. What is the GCD of both these? 1. This is A and C. And when I multiply this A and this C with A and B, this must be equal to GCD of A and BC. Here you can see that GCD of this is equal to GCD of A and B multiplied GCD of A and C. Both product is 3 and this is 3. Okay, we prove this. For this, we suppose that AB GCD is 1, D1 and AC GCD is D2. If A and B have GCD D, suppose it is GCD when it satisfies 3 conditions. What are the 3 conditions? D must be greater than 0, D divides A, D divides B, common divisor of both, and there exists an other common divisor other than D belongs to set of integers such that C divides D. Okay, C divides A and C divides B. This is common divisor. Then C must divides greatest common divisor. If some number satisfy these 3 conditions, then we can say that this is the GCD of these two. Sorry. Here we suppose that GCD of AB is D1 and GCD of A and C is D2. As you know that case first, D1 is also greater than 0 and D2 is also greater than 0. Therefore, their product d1 and d2 must greater than 0. This is our first condition. When you are solving this question in paper, don't make this circle, this rectangle. I make it just for clear understanding. Now we have here second condition. We have to prove second condition from this. If A and B GCD is D1, therefore D1 divides A and D1 divides B. Also D1 D2 divides from here. If D2 is GCD, greatest common divisor of A and C, then D2 must divide A and C. D2 divides C. If D1 divides A and D2 divides divides A, then their product must divide A. For example, if 2 divides 10 and 5 divides 10, then their product must divide 10. Okay. Also, if 2 divides 6 and I take any other number, 4 divides 8, then their product must divide their product 48. Okay. So if D1 divides B and D2 divide BC, then their product must divide this multiple product. Okay, multiple of B and C. As you know that this is the second condition, D1 D2 satisfied. Actually, what we are going to prove that its GCD is D1, its GCD D2, then A and BC if have GCD of D1 D2. What we have to prove, GCD of A and BC must be D1 D2. Now we satisfying the three conditions of GCD. What is the third condition? Third condition is, then there exists C belongs to set of integers, any other number. You can also take T, any number, you can suppose any number. T belongs to Z, set of integers, then T must be common divisor of these two, because we are going to prove this is GCD. So we take a common divisor other than D1 D2, T. So T divides A, T divides A, T divides A and T divides BC. T divides A and T divides BC. Okay. If T divides A, then if T divides product of BC, then T divides B or T divides C. Clear this point from here. If 2 divides 16, or you can take 14. If 2 divides 14, then 2 divides 2 or 7. If both are relative prime, BC is relative prime here. BC is relative prime. B and C have no common divisor greater than 1. So if I take here two relative prime numbers, then any number divides their product, then this number must divide only one number, not both of these numbers, because they are relative prime. So case first here, what is case first? Case first is case first case first is t divides a and t divides b. In these two, I take only one case, t divides b. If t divides a, t divides b, t must divides d1 because t is common divisor and d1 is greatest common divisor. So common divisor divides greatest common divisor, and then t must divide d1 d2. If 2 divides 8, and if with any number I can multiply, 2 must divides their product, 5 6 7 8, any number. So this t divides d1 and d2 in this case. This is also third condition. Now case second. What is the case second? If t divides a and t divides c in both this. If t divides a and t divides c, then t is the common divisor of a and c. Therefore, then t must divide greatest common divisor of a and c. What is greatest common divisor? d2. If t, which implies t must divide d1 d2. If 3 divides 6, then 3 divides 6 and multiply with any number. You can multiply with any number. 3 must divide their product. So this is what we proved here. This is also this case second, third condition. Then we prove here three conditions of GCD. GCD must be greater than 0. GCD must divide both of those numbers, and there is a common divisor other than greatest common divisor d1 d2. Okay, so what we prove that a and b c is their GCD of a and b c is d1 d2, which means a b and a and c. This is our required result.